I've been working with monitoring in Python specifically for past 5 years or so, and with OpenTelemetry for the last 2 years. Yeah, I do some open source in my free time, mostly around monitoring and all about Python mostly. Yeah, and my day-to-day job is integrating Dynatrace with different technologies which we do not yet monitor. So the agenda, table of contents of today's talk is pretty simple, straightforward. We will talk about the basics of OpenTelemetry. What is it? How it works? Why do we need it even? We will talk about instrumentation, and we will take a look at some of the examples that are there. And at the end, we will take a look at the distributed tracing. So that's actually why OpenTelemetry was created. And we will take a look at a couple of interesting examples there as well. So back to the basics, right? OpenTelemetry 101. How did it came to be even, right? Where did it come from? So there was a project which was first released, I believe, back in 2016. It was called Open Tracing, open source project, which was based around doing tracing, essentially. It was a standard, a set of libraries. They supported several languages. It was all about tracing. And then there was another project which started later by Google. It is called Open Census. It's more about collecting data, and it was basically a fork of internal Google project called Census. So two projects basically coexisted for some time, and that was awful. And let me tell you why. Because both of them were kind of good in what they do. So you as a developer had to choose which project to use for your observability. And that was a hell of a headache. Almost like a holy war between fans of one technology versus the other. So what did they do? They took two technologies and they merged them. I have an open tracing, I have an open census, boom, Apple Pen. No, not really, open telemetry. And that's great, because now we have one project and it's an open standard. Dynatrace actually contributes to the development of OpenTelemetry. This is how I got in touch with it, at least. So let's talk about observability and why OpenTelemetry came to be. When we talk about microservices and when we think about them, we basically lose all the usual monitoring approaches which we are used to. Like, imagine you collect logs from one microservice, from a monolith, right? And everything is in place. Like, it's a single-threaded monolith, for example, maybe a multi-threaded. You can figure out almost every issue based on just the logs and metrics, maybe. But when we switch to microservices, now you have all sorts of issues. Like where did the call break? Which microservice failed? Why did it fail? How much time it took for a certain step to finish? All kinds of problems. And OpenTelemetry aims to fix them and to address them. How does it do it? So with OpenTelemetry, we collect traces. Traces is like a representation of what was done throughout several services. I have a small picture here where you can see that for the whole duration that client called our API, we did a bunch of tasks in the background, like authorization. We went through payment gateways. There was a call to database. There was a dispatch to the workers, and so on. And this is essentially what Trace allows us to do. We can also collect metrics. it's basically, it can be a replacement for Prometheus, for example. We can collect logs using OpenTelemetry, although I have to say that at the moment for Python, logs are in a beta state, so they are not ready for production yet. And you can also collect all kinds of contextual information throughout your trace. Here is what an example of trace looks like. It's basically a JSON with a bunch of information like what is the context, when was it created, so it's time-stamped, and you can attach a bunch of attributes to it. You can use, you can even assign events to it, so it can almost serve as a replacement to logs without using any additional monitoring technology. OpenTelemetry works in a quite straightforward way, very familiar to those who worked with something like Prometheus. We have an application for which we install an SDK, like a library. It exports the data. Not necessarily you can pull data from the application just like you do with Prometheus, but usually it's an exporter. You can have a collector in the middle, not necessarily, but an option. And at the end, it ends up in some kind of backend when you store these traces. Like in AWS, you have X-Ray, you have Zipkin, Jagger, so many different options. I also have this diagram which shows you an overview, like many different parts of the system can be traced, and they all end up in the collector. So OTel is a short for OpenTelemetry. So let's talk now about instrumentation. We will take a look at some of the examples. OpenTelemetry comes with auto-instrumentation in place. So this is really cool because you don't necessarily have to change anything in your application. Here is a small example. We have a little Flask application which just exposes one route. And what we do here is we sleep randomly from 1 to 6 seconds, nothing fancy. And that's like an entire code for this application. So in order to make it work, you just need to install a couple of libraries. There is a library for almost every Python backend framework. There is a library for Django, for Fast API, for Flask, and for some others. Like you can instrument Celery, for example. So once you install these libraries, you can just invoke your application with this toolkit called OpenTelemetry instrument, which just uses all this interjection done by the SDK and collects traces automatically from everything. So let's take a look at the example. I have a small setup right here. It's just it's the same Flask application we talked about. So what I'm going to do is I'm going to invoke it with this command, which I showed you. I have a virtual environment in which all these libraries are installed, everything is set up. So once I do that, obviously application starts. I now have a Flask web server running on my local host exposed on this port. So let's invoke it. It sleeps, obviously, for some time. So it says, okay, I slept for 5 seconds. Nice. What do we see in the console now? Here is our trace. So this was done automatically by OpenTelemetry. We have a whole bunch of attributes like what was the user agent of the browser, whole set of attributes. For example, we have a status code, timestamps, attributes of OpenTelemetry itself. So that was all done automatically, and it works even between different microservices. So if you instrument 2 different microservices automatically, then this trace will travel from one to another. Yeah, I basically ruined the joke here. Ladies and gentlemen, we got them, the traces. So just to recap, in order to do auto-instrumentation with OpenTelemetry, you have to install a set of libraries. They all come with the OpenTelemetry distro, so not necessary to install them separately. You can also, and you can run it using this tool, and you get automatic instrumentation out of the box. All right, so now let's go to the manual instrumentation. That's a bit more fancy. So when you want full control over what is it you are tracing, that can be a preferable option. So we will take a look at a couple of examples. I have another Flask application here with a bunch of methods, a couple of roads. And in order to instrument it manually, I will use this thing called tracer. It's like almost like a global object in Python. Once you import it from OpenTelemetry SDK, you can then start spans. So span is like a unit of work which does something. It represents a unit of work in the trace. And you can nest spans into one another. We will get back to it later. So in order to instrument this example application, I can just use either a decorator or a manual tracing. Here is how it looks like. I decorated a couple of methods with a decorator and gave each decorator a name. So for example, thinking time has a thinking time name, and that's how it will look like in the actual trace when I run it. For the roads, however, I chose to use the with statement, which has the exact same effect. You don't necessarily have to settle for one or another, whichever is more convenient for you. So I've talked about nesting spans into one another. What is it? So naturally, when you think about several units of work, like we compute something and there are separate chunks of this computation. Like first we do this work, then we use that data to do another work, and you can represent each one of them as a span. And they can all be children of a parent span. So that's how you can build a nested spans to result in a trace, end-to-end trace. There is one other option, linked spans. It is not supported in all OpenTelemetry backends yet, but it probably will be soon. So you don't necessarily have to nest spans into one another. You can just link them, and they will be linked in the visualization as well. So comes useful from time to time. And finally, cross-service spans. That's where distributed monitoring comes into play. This is like a classic story of microservices. Right now we are talking about just HTTP-based calls, so from one microservice to another. We can chain them one by one. So, for example, right here I have a method, a road called gather external data, which in turn calls another service get stocks. So it retrieves something about stocks. And how do I make OpenTelemetry work with that when I do a manual instrumentation? I want the context from the parent microservice, which called the second service, to be propagated to the called microservice. and it has to preserve the entire context. It has to understand that it's the same trace. So OpenTelemetry has this thing, it's called propagator. There are several approaches how to do that. The simplest one is just to import a propagate object from OpenTelemetry, and you have to call a couple of methods. So in order to preserve a context in a propagator object, for example, you can use headers as context preservation storage. You inject the current state of the span into the headers, and then you extract it in another service. And in this way, the context of your trace is preserved within the headers when when microservices call one another. And here you can see a little picture what it results in. Right. So a slightly other topic. It's a bit more difficult. So distributed tracing with queues. When it comes to distributed tracing with asynchronous execution between microservices, you can't use HTTP calls, right? Each of your microservices actually produces a message which is then stored in a queue. It can be Kafka, it can be SQS, it can be RabbitMQ. So we basically work with workers which execute these tasks which are scheduled by some service or by another worker. And to do that, you have to take into account what is it that you use. So for some Python backends, it's quite straightforward, but it really boils down to what queues you use and what kind of information you can put into a message. So for today's example, I'm going to use Redis streams specifically for storing the messages. And I'm using Dramatic as a scheduler worker instead of Celery. I'm not a big fan of Celery, to be honest. Here's how it works. So for this example, I'm using a slightly different approach. I'm using a class called trace text propagator. It gives you more flexibility when it comes to injecting the trace, and an object into which you inject a trace is called carrier. This is just a notation. Carrier can be just a dictionary. You take current context of OpenTelemetry. It's very easy to obtain it. I didn't include it in this code, but it's quite straightforward. You inject it into this dictionary, and then you can just add this dictionary into the message which you store in a queue. The important thing is that it must be serializable. Thankfully, OpenTelemetry traces are just basically JSON or Python dictionaries with a simple types like Boolean, string, numbers, and nothing fancy, date, time. And they are perfectly serializable into JSON, which means they can be safely stored in a queue such as Redis streams. So in this example, I enqueue this message using Dramatic, and what I have to do then is to extract it in a worker. So imagine you have an API, and you send you schedule a task using this API, something which takes a long time, like generate reports for entire months. It takes an hour. So you have an API where you send this request, it reports, yeah, all done. I have scheduled the task, 201, accepted. You are happy, the task is scheduled, and the context which is generated with this task is stored within the message, which is in the queue. The worker then picks up that message, and when it parses the message, you can extract this carrier object and just take out the context of the trace out of it. There is one cool thing which OpenTelemetry for Python allows you to do. You don't necessarily have to pass this context object manually into each following trace. You can just set it as current globally active context. Of course, it gets a little bit more complicated when you think about like which objects are which threads are exposed to this object. But for the simplicity's sake, when you call this attach method, it just automatically assumes for the entire context of the execution that this is the current context, and it works great with workers. Yeah, so let's take a look at the example. First of all, I'll just show you what a trace looks like in something like a Jagger, which is one of the traceability backends compatible with OpenTelemetry. The way I run it all in my example is I have a Docker compose. There is an API, which is a fast API application. It's exposed on this port, and yeah, it just schedules the tasks. Now the other thing I have is worker. It is not exposed to any port, and it's basically the same container, the same application, but designed to run as a worker. So when I send a message from API, when I schedule it, the worker will pick it up and execute it. I also use Redis, which is like the most straightforward deployment of Redis you can think of, and a Jagger. So for Jagger to work for Python tracing with OpenTelemetry, you need to expose a couple of ports. This one is for the UI, and this one is for the trace injection. So usually, even in the OpenTelemetry documentation, there are like 20 ports exposed and mapped to the local host or to your server. There is no need to do that. It's not documented, but you just need a couple of them. You don't need all the others. So in this example, right, in my worker, I actually load several machine learning models, some transformers, keyword extractors, and here is what this trace gives me. Let's take a look at the example in the code. So here is my code for loading these natural language processing models. I initialize NLTK, spacey, but here's how I do it. I start a trace, and then I nest another trace within it. And the same for spacey, the same for sense to vec, same for sentence transformers, and so on. And that's it, essentially. I didn't do anything else other than initializing this tracer object. It works the exact same way as a logger, very familiar approach. And it results in this picture. So backend Jagger visualizes it for me, and now I have a perfect visibility into how much it took for the entire set of machine learning models to load in my Docker container. So for example, I now understand that sense to vec takes most of time, almost 3 seconds, and maybe I have some room for optimization here. I know what you're thinking. Wow, right? Yeah, that was my first impression when I saw this technology as well. I thought like, damn, that's pretty good. But it doesn't end here. What we are going to do now is we are going to run a quick example. I have an actual API of the code which I showed you exposed here. It works with actual Firebase. It works with the queue. It works with cloud storage. So let's just quickly check that it works. Yeah, all healthy. And now what I'm going to do is I'm going to schedule a resource to be processed. So once I do that, it will be scheduled in a queue, and the message will wait for the worker to pick it up. The context of this trace is created on the API side, in the API container, but it will be propagated into the worker container and we will see a single trace. Let's try it out. Execute. All right, a successful response. Now I will probably see a trace here. Yeah, here it is. It's in progress. It actually builds up while I'm talking because the processing goes on and goes on. So right now the last span is called normalize noun chunks. That's something we do when processing text. If I update it, all right, we are at another span, analyze keywords. That would actually take probably longer. If I remember correctly, this whole thing takes about 30 seconds or 60 seconds. Yeah, and it's complete. So we have an entire trace propagated from API to the worker. We can see that the worker took 40 seconds to do its job. The API took just under 700 milliseconds. I can recognize that analysis of the resource took the longest, and specifically within this part of code, transformer models took most of the time. So that's something to think about for the developer, like do we need that? Can we optimize it? Let me just show you a piece of code which actually does it. So you can recognize the names of the spans. And right over here, I do an actual encoding somewhere. Yeah, here it is. So this is a span called transformer encode. I call it transformer model and ask it to generate nearest neighbor KNN, basically vectors. And it takes a long time. So that's what my trace is showing me. So now we can see that it works between asynchronous distributed microservices. And I know what you are thinking. Wow, right? Yeah, that's pretty good as well. But it doesn't end here. What you can do with OpenTelemetry, you can automatically generate a view between different microservices, see how they are connected, which microservice calls which one. Let me show it to you. That's a pretty solid architecture right there, right? And I know what you're thinking. Dave! Yeah. So yeah, that's basically it. I wanted to take a moment to thank my colleague and friend Radu Stefan for his help in preparing for this presentation. And let me know if you have any questions. Thank you.
Yeah, as a matter of fact, we do have a few questions. So Wendy pointed out that in some cases there's user-specific data that we don't want to expose in such logs. And how does OpenTelemetry handle data anonymization?
Yeah, great questions. OpenTelemetry doesn't handle anonymization in any way. So you do not really expose data, you just expose spans. It's your choice to attach certain data as event or an attribute to the span. You don't have to do that. So by default, the only thing you actually see are the spans. So there is nothing about which user actually called it, despite the fact that I have this information in the worker and API, like I do not allow the call to be performed unless you are authorized with a token, but this information is not exposed by default. You have to actually manually, explicitly do it. The other question is how does it affect performance? So this is an important one and it's resolved in a pretty good way. When you configure OpenTelemetry, you are able to set sampling rate. So how many calls are actually traced? Here's how I do it in this example. when I configure OpenTelemetry, I'm setting a sampling rate, and I defined it as 1%. So 1% of all calls is traced. You might ask, but what if there is an error, right? Something failed within the trace, and I didn't catch it. How do I handle this situation? Well, don't worry, it was a problem several years ago, but it's not now. OpenTelemetry is smart enough to figure out that if there is an exception, then this trace will be sampled. So that's you can configure it almost in real time with sampling rate.
Yeah,
Okay.
the next one is about Sentry. How OpenTelemetry compares to Sentry? Is it better, worse?
Well, I say use both. So that's what I do. For instance, Sentry does not conflict with OpenTelemetry. They work perfectly together. Sentry is a really good application, right? It's and Armin Ronacher works for Sentry. Like, if you are not using Sentry, come on, it's a good product. And it's a really good solution to capture your uncaught exceptions, right? This is why it was created in the first place. They do tracing now, and so forth, but you can still use it at least for exception capturing. And at the same time, rely on OpenTelemetry, which is an open standard, interchangeable between different languages and technologies. So it's not just for Python, to do actual tracing and observability.
How to use OpenTelemetry when the app is run with servers like Unicorn, Uvicorn?
Yeah, you don't need to do anything special for that to work. Let me show you. It actually runs as Unicorn, and it can run as GUnicorn. So here is an example. I just launched it, right? So Uvicorn is an executable. It imports an object of the application. During the import, initialization of OpenTelemetry happens, and then within Uvicorn or GUnicorn, whichever you choose, a separate thread is created, just like for Prometheus, which exports the observability data. So it works just out of the box. You don't even have to do anything special.
Another comparison this time to Datadog.
So, yeah, for example, in Dynatrace, we have a thing called pure pass. It's the same thing, basically. It's a tracing. And we had it long before OpenTelemetry was even a thing. So when you lock on a specific vendor, such as Datadog, you are basically just with them. You have to continue using Datadog for these purposes. Dynatrace, for example, switches and encourages people to switch to OpenTelemetry because that's interchangeable. That's why we actively contribute to this project. So it's just, it's like choosing whether to use a very specific vendor or using an open standard. I think it's a pretty obvious choice.
Unfortunately, we were 8 minutes past time, so
okay.
Yeah. Thank you again.
Yeah. I was going to say, ping me on Twitter if you have any special questions, and I will be around. Thank you, guys.